What is aluminum? Aluminum is a chemical element with the symbol Al and atomic number 13. It is silvery white, soft, non-magnetic and ductile metal in the boron group. By mass, aluminum makes up about 8% of the Earth's crust, where it is the third most abundant element and the most abundant metal. This is the example of the aluminum. Next, we will learn about the properties of aluminum. Physical properties of aluminum isotopes. Only aluminum-37 is stable. Other isotopes of aluminum are radioactive. Aluminum atom has 13 electrons, and it is low density and has ability to resist corrosion. Chemical properties. Aluminum has a high chemical affinity to oxygen, and aluminum is used as a reducing agent in the Thurman reaction. Aluminum reacts with the most nonmetals upon heating.
Hello guys, so what is silicon? Silicon is a chemical element with the symbol Si and atomic number 14. It is hard, brittle crystalline solid with a blue-gray metallic luster and is a trivalent metalloid and semiconductor. It is a member of group 14 in the periodic table. So this is how silicon looks like. And from group 14 in the periodic table. Silicon, it is most widely distributed in dust, sands, planetoids, and planets as various forms of silicon dioxide, or we can call it silica or silicates. More than 90% of the Earth's crust is composed of silicate minerals, making silicon the second most abundant element in the Earth's crust, about 28% by mass, after oxygen. So we have solar cells or semiconductor silicon, and we also can get silicon. So what silicon used for? The element silicon is used intensively as a semiconductor in solid-state devices in the computer and microelectronic industries. They are used to make dynamo and transformer plates, engine blocks, cylinder heads, and machine tools, and to dioxide seal. Silicon carbides are important abrasives and are also used in lasers. Silicon has a solar band efficiency of 1.1 electron volt, which makes it a reasonable option to be used as solar cells and solar panels.
Here's diagram of aluminum silicon. Aluminum silicon binary system. The system contains two solid solution phases of aluminum and silicon, which are alpha and beta. Alpha is a solid solution of silicon in aluminum with maximum solubility at 557 degrees Celsius with 1.6% silicon, while beta is a solid solution of aluminum in silicon with maximum solubility at 557 degrees C with 0% aluminum, which means is pure silicon. Eutectic alloy in aluminum silicon system contains 12.6% silicon. The eutectic reaction of aluminum silicon system is liquid reversible to alpha plus beta. The eutectic aluminum silicon contains an eutectic microstructure, which is a lamellar microstructure. There is an example of micrograph of aluminum silicon eutectic microstructure. The lamellar structure is an alternating layers of alpha and beta crystal. Eutectic has the lowest melting temperature, which is 557 degrees Celsius. When solidifies, molten aluminum silicon alloy will transform. into lamellar structure at a constant temperature which is 557 degrees Celsius. The concentration of alpha phase is 1.6% silicon, while beta phase is 100% silicon.
What is normalizing? Normalizing is a heat treatment process that is used to make a metal more ductile and tough after it has been subjected to thermal or mechanical hardening processes. Normalizing involves heating a material to an elevated temperature and then allowing it to cool back to room temperature by exposing it to room temperature air after it is heated. This heating and slow cooling alters the microstructure of the metal, which in turn reduces its hardness and increases its ductility. So if you can see the graph there, the normalizing occur above A3 and ACM. So you can see the normalizing occur at the red dot line, which is above AC3 and ACM, that have been labeled there. So that was normalizing occur. A heat treatment process consisting of alternatizing at temperature of 30 degrees Celsius to 80 degrees Celsius above the AC3 transformation temperature, followed by slow cooling, usually in air. The aim of which is to obtain a fine-grained, uniform distributed ferrite pyrrolite structure as the diagram below. So you can see F is a ferrite and P is pyrrolite. So that's the aim of this process, normalizing. Normalizing is applied mainly to unalloyed and low-alloyed hypoeutectoid steels. For hypoeutectoid steels, the alternatizing is 30 degrees Celsius to 80 degrees Celsius above the AC1 or ACM transformation temperature.
Quenching. It is a process that decreases fluorescent intensity of given substance. There are 4 types of quenching. The first one is concentration quenching. At low concentration, linearity is observed. But as the concentration of the same substance increases, the fluorescent intensity decreases. The second one is chemical quenching. It may be of various factors like pH. Aniline at pH 5 to 13 gives blue fluorescence when excited to 290 nm. The second one is oxygens. Presence of oxygen led to quenching because of its paramagnetic property. The third one, halide. Halide like chloride, bromide, iodide, and electron withdrawing group like nitro decrease the fluorescent intensity. The last one is heavy metals. Presence of heavy metal also lead to quenching because of collision and triple ground state. The third factor, static quenching. In this process, quenching agent form a non-fluorescent complex with quenching agent. And the fourth one and the last one is collisional quenching. Quenching takes place when number of collisions are increased due to several factors like presence of halides, heavy metal increase the temperature and decrease in viscosity. And the last one is factor affecting quenching. pH, oxygen, temperature, halide, heavy metal, electron withdrawing group 6.
What is tempering? Tempering is a process of improving the characteristic of a metal, especially steel, by heating it to a high temperature through below the melting point and then cooling it slowly, usually in air. The process has the effect of toughness by lessening brittleness and reducing internal stresses of the metal. So, for the basic understanding of tempering, if at first we have to heat at a high temperature and then cool it at slow down. So we have a different type of hardness as we can see of the next slide. So basically tempering is we are tempered at a temperature 300 degrees Celsius to 400 degrees Celsius and the soaking time about 2 hours of 8 hours depending on the part size. At these temperatures, martensite transforms to troostite. It is very fine and troostite is softer than martensite and also more ductile. Tempering at a temperature more higher than 400 but lower than critical point, it will produce a sorbite. About soaking time 2 to 8 hours depending on the part size, and then sorbite will become out. As we know, sorbite and troostite are principally similar structure, differing only in the particle size. And we can know sorbite is more ductility and toughness and less strong than troostite. So when we can compare of ductility comparison with this, the ductility, sorbite is more ductile compared to troostite, and troostite is more ductile compared to martensite. This different type of martensite, troostite, and sorbite is come from because we temper at a different temperature.
Annealing is a heat treatment in which metal is heated to a temperature above its recrystallization temperature, kept at that temperature for some time for homogenization of temperature, followed by very slowly cooling to develop equilibrium structure in the metal or alloy. The steel is heated to 30 to 50 degrees Celsius above A3 temperature in case of hypoeutectoid steel, to 30 to 50 degrees Celsius above A1 temperature in case of hypereutectoid temperature. The cooling is done in the furnace itself, and the aim of annealing is the first one is to increase ductility, improve formability, reduce hardness, recrystallize cold work, remove internal stress, increase toughness, decrease brittleness, increase machinability, decrease electrical resistance, and improve magnetic properties. Full annealing. It is a process where steel is heated from 30 to 50 degrees Celsius above AE3 temperature in case of hypoeutectoid steel, and 30 to 50 degrees Celsius above A1 temperature in case of hypereutectoid, keeping it at that temperature for some time for homogenization, followed by cooling at very slow rate. The cooling may be about 10 degrees Celsius per hour. The aim of full annealing is to get all the changes in properties of the metal, like producing equilibrium microstructure, increase in ductility, reduction in hardness, strength, brittleness, and removal of internal stresses. The microstructure after annealing contain coarse ferrite and pearlite. Stress relief annealing. In stress relief annealing, metal is heated to a lower temperature and is kept at that temperature for some time to remove internal stresses, followed by slow cooling. The aim of stress annealing is to remove internal stresses produced in the metal due to plastic deformation, non-uniform cooling, phase transformation, and no phase transformation takes place during stress relief annealing. Spheroidizing annealing is where the steel is heated to a temperature below A1 temperature. Keep at that temperature for some time, followed by slow cooling. The aim is to improve machinability of the steel. In this process, cementite is converted into spheroidal form. The holding time varies from 15 to 25 hours. Process annealing is where the cold work metal is heated above its recrystallization temperature, kept for some time followed by slow cooling. The aim of process annealing is to restore ductility of the cold work metal. During process annealing, recovery and recrystallization take place. New acquisite strain-free grain deployed at high stress region in the cold work microstructure, and hence hardness and strength decrease, where ductility increase.